Hi, my name is Dominik Dvorak. I'm from the AIT, the Austrian Institute of Technology, and my talk will be about multiphysical battery modeling for predicting the aging behavior of lithium-ion batteries.
Okay, so welcome everyone to the last session, to the last presentation of this session. This presentation will be about SystemModeler again, using the electric energy storage as library for aging prediction of lithium-ion batteries. So I'm, like my colleague Dragan Simic from the Austrian Institute of Technologies, from the Electric Drive Technologies business unit. So first, let me give you a short overview about this presentation. I will start with some motivation. So why we're simulating and why is it necessary to be able to simulate the aging behavior of lithium-ion batteries. Then I will tell you the approach we're using, the Arrhenius equation, followed by some words about our electric energy storages library, which is a multiphysical library for simulating the operating behavior of batteries. Then I will follow up with simulation, with a description of our simulation models, and finally scenario definition and simulation results, and then the outlook. So let us begin with the current challenges of electric vehicles. As you might know, I'm as well, like my colleague, from the automotive domain. And due to the increasing environmental awareness of the people, electric vehicles become more and more popular these days. As a proof of this, we can see that there are a lot of different electric vehicles on the market, and each big manufacturer has his own electric vehicles. Critical factors for success are currently the costs of electric vehicles, the range of electric vehicles, charging time, and safety. And if there's any problem with any of these parameters, people won't buy electric vehicles. So it's really hard issues, but we're just at the beginning of the kind of electric era. Solution approaches to overcome these problems are to use lightweight components, to use novel heating or cooling concepts to increase the range, so to optimize the energy efficiency of electric vehicles, and to do so to increase the range of the electric vehicles. To investigate new battery technologies to increase the energy or power density of lithium-ion batteries, or to optimize the operating strategy and do some thermal management in order that the components don't get overheat and get damaged during operation. And as this presentation is about lithium-ion batteries, I want to say that the last 4 points, which you can see here, apply for batteries as well, or in special. Because aging mechanisms of lithium-ion batteries are mostly affected by the battery temperature and the battery state of charge. And with the last 4 points, bullet points, you can really optimize the state of charge and temperature you're operating your battery in. So for safety and performance reasons, it is really necessary to understand aging mechanisms and aging effects during operation of batteries. So let's have a short look of which aging effects we're talking about. So basically we're talking about calendaric and cyclic aging effects. Calendaric aging effects are those effects which happens regardless of whether you use your battery or you just store the battery within the case and you don't draw current out of the battery. No matter which aging effect you're looking at, it's all based on degradation, which is a physical or chemical change in the active material of the batteries. And this happens due to parasitic chemical side reactions during operation. The results which you can observe when it comes to battery aging are on the one hand capacity loss, so you can get at the end of life, so we've got a illustration here. At the beginning of the life, you have a certain internal resistance and a certain capacity of the battery. And at the middle of life, and especially at the end of life, the internal resistance of the batteries will increase, while the capacity, so the charge you get out of the battery, will decrease. So now you might ask, who cares? And I will tell you, vehicle manufacturers care, because if you underestimate the battery lifetime, no one will buy an electric vehicle. Because if, for example, BMW claimed that the i3 would have a guaranteed lifetime of 1 year, no one would ever buy a vehicle for 10,000s of euros. While on the other hand, if you overestimate the battery lifetime, no one will ever buy an electric vehicle again. Because if BMW said the i3 had a lifetime of 30 years, and people might be interested and buy this electric vehicle, and then the vehicle stands still after 8 to 10 years, they won't buy an electric vehicle again, and you lose your future. So this is why it's really necessary to understand battery aging effects and to be able to predict the aging behavior. So how do we do that? I'm going to show you a very simple approach, which we're using at the AIT. This approach is called the Arrhenius equation. This equation basically says that the aging rate is really dependent on the battery temperature on the one hand, because the side reactions or the reactivity of the active material really depends on the battery temperature. The extended approach also considers the state of charge as an important parameter for battery aging. And it also claims that aging effects slow down over time, because you lose over time due to aging effects active material, which you can use. So the energy you can take out of the battery will get less and less. But this also means that the energy which is available for the parasitic side reactions will decrease as well. So the aging effects slow down over time. So we've got here this very simple equation, which tells us the aging rate of batteries with regard to the state of charge, the temperature, and the time. And I've got here some illustration, 4 scenarios for different state of charge and different battery temperatures. And we see here that the temperature has really a very high impact on the aging rate. So we've got here an aging factor. A doubling factor means that the battery aging mechanisms take place at a double speed. And we see here that the temperature has a very significant impact on the aging behavior of lithium-ion batteries, because those two graphs are at a state of charge of 0.5 and a state of charge of 0.8. At a temperature of 40 degrees, the aging rate is much higher than at the same state of charge at a lower temperature. So to overcome those problems and to simulate the aging behavior of lithium-ion batteries, we developed a battery library, which is called the Electric Energy Storages Library. We developed that for extensive applications. So we want to use our library in a flexible way for different simulation scenarios. And we wanted an easy configuration of our models, so we really put some effort in the parameterization of our models to make it very intuitive in usage, and also to provide simple usage. So just to drag in the components in your basic model and to have ready-to-use drag-and-drop models. The main use cases we developed our library for are, on the one hand, electric simulation of batteries. On the one hand, it's thermal investigation, so thermal behavior and for example, to consider cooling circuits of batteries, or to consider the heat up, or to determine hotspots during heat up phases, and so on. The third use case is the function development of, for example, of a battery management system. And the fourth use case is the aging prediction, with this presentation is about. We see here a possible application scenario. Our battery model in an electric we used the battery models for an entire vehicle simulation, and we had the battery stack below the vehicle, and we used our electric energy storages library for electric and thermal simulation. We built the whole library on a modular structure. As we can see here, the basic concept, we've got an electric model which maps the dynamic material characteristics to an electric equivalent circuit. We've got also a thermal model for simulating the thermal behavior, and a parameter adaptation model, which is kind of the heart of our battery models, because this model calculates the parameters of the electric equivalent circuit with respect to battery aging, with respect to temperature, and to the state of charge. We've got also some integrated parameter sets for lithium iron phosphate batteries and nickel manganese cobalt batteries. As I said before, the battery models, the electric models, are based on an electric equivalent circuit. You can simulate either a static, so very simplified models for a large number of battery cells, so it's a very quick model. But you can also use dynamic models which are very accurate in generating results. You can simulate on cell or on stack level, so you can have a serial or parallel connection of single cells. And you have, in the thermal model, scalable prismatic or cylindrical cell models. So you can scale the battery in size, and you have thermal conduction or convection, heat capacity, and so on. And you can build with that a thermal stack, including cooling system, for example, to analyze the impact of different kinds of cooling systems, so air cooling or water cooling or something like this. And we've got the aging block, which considers the calendaric or cyclic aging of the batteries. So we can see here a screenshot of a cell model implemented in Modelica and SystemModeler. We've got here the parameter adaptation model, which adapts the parameters and configures the electric model, which we have here. So it's a very simple model, which is very good for the automotive application. So it's very sufficient, very fast, and it has sufficient accuracy for the automotive domain. We've got here an open circuit voltage, then a serial resistance, and up to 2 RC circuits to consider also relaxation and double layer effects within the battery. We've got here a heat port, which is the interface to the thermal model, as we see here, so which is indicated by this arrow. And here we see the structure of the electric energy storages library. So basically, we've got here the main package is the batteries package, which consists of the cells, the stacks, and the components of which the cells and stacks are composed of. So to enable the user to build his own models out of our components. And we see here the impedances, parameter adaptation models, diagnostics, the aging block, and the thermal models. So how did we apply our electric energy storages library? We have successfully applied our library for investigating the effects that vehicle-to-grid scenarios have on the aging effect of lithium-ion batteries. For those who don't know, vehicle-to-grid scenarios or vehicle-to-grid strategies are that if an electric vehicle is connected to the grid, it cannot only be charged by the electric grid, but only support the grid during peak power periods. For example, in the evening when when the people come home from work, the required power from the grid is higher, and so the electric vehicles connected to the grid can support the grid during those periods, which means an additional cyclic charge of the battery. So therefore, we assumed a battery with an energy content of 25.6 kilowatt hours. We had a look at, or we used a driving cycle which we extracted from daily trips at a given driving distance. Therefore, we used a frequent driver profile of Austria. So it's about 60 kilometers long. And for some scenarios, which I'll explain in a second, we considered the vehicle-to-grid scenarios for supporting the grid, as I said, at peak power periods. So those are the 5 scenarios we had a look at, we simulated. The normal use scenario doesn't use vehicle-to-grid and is a kind of reference scenario. So we drove about 60 kilometers per day, and we charged our battery whenever grid was available. So either when the person was at work or when the person was at home. The second scenario is a controlled charge scenario, which as well doesn't use vehicle to grid. We have again a driving distance per day of 60 kilometers, but we charge the battery only when the grid is ready. So if we're in a peak power period of the grid, we won't charge our vehicles. The third scenario is the first vehicle-to-grid scenario, the kind of normal vehicle-to-grid scenario. There we charged about 6 kilowatt hours per day, where we supplied 6 kilowatt hours to the grid and recharged those 6 kilowatt hours. The driving distance we considered in this example is again 60 kilometers, and we charge when the grid is ready. The fourth scenario is the vehicle-to-grid short distance scenario, which is quite equal to the normal vehicle-to-grid scenario, but with a decreased driving distance of only 30 kilometers per day. And the last scenario, the fifth scenario, is a vehicle-to-grid scenario with peak power load, where we supplied only half of the energy to the grid, but at a higher rate, at a higher power rate. So we've got here only 3 kilowatt hours per day charged into the grid and charged back afterwards, but with a required power of 6 kilowatt. And the rest of the parameters are like the normal vehicle-to-grid scenario. We used also some environmental conditions. Therefore, we used the daily temperature in Linz, which is in Austria, and we used the average temperature of the years 1971 to 2000. We've got here this temperature curve in order to be able to consider the different temperature aspects during different times of the year, because the aging effect, you must investigate aging effects true enough over longer periods of time, and so we had to take into account the varying ambient temperature as well. So here is basically the implementation of our Modelica model in SystemModeler for the vehicle-to-grid scenarios. We've got here the thermal aspect, so the temperature profile of Linz directly connected to the cell. So it's a very simplified model only, but we could generate good results with that. You see here the link between the thermal model and the electric model, just connected via a thermal connector via a heat port. And we've got here the electric load with a current, with a constant current, constant voltage charging strategy, and the power load, which is either the vehicle-to-grid scenario or the driving cycle, which we have applied to the battery. And we've got here a control table and some control strategy which determines whether the driver is driving to work or whether the driver is going home or or whether the battery can be charged. This takes place in the rest of the model. And now let's have a look at the results we generated. So first we had to parameterize our aging model. Therefore we used some cell measurements which took place over 105 days. We had cycling data of 1,800 full electric cycles. And here we see an example of the how we parameterized our Arrhenius equation model. We've got here 3 different measurements at 3 different temperatures, so at 60 degrees, at 45 degrees, and at 23 degrees. And the bullet points are the measured results, and we fitted a curve to get the parameters of the Arrhenius equation. So using these parameters, we performed a simulation of our 5 simulation scenarios and made some prediction based on these initial measurements. We considered the thermal aspects and the state of charge as well. So what we can see here in the results is the lifetime or the predicted capacity loss during the 5 application scenarios. And what we can see here, so okay, first of all, I want to mention in the automotive domain, you say that the battery, you cannot use the battery anymore if a capacity was reached, which is about 80% of the initial capacity. And if we take this value, we see here that in the best case scenario, which is the controlled charge scenario, and it's pretty much the same as the vehicle to grid short distance scenario and the normal use scenario, so they're pretty at the same level. The battery would last for about 6.5 years. But if we considered another scenario, so the worst case scenario, the normal vehicle to grid scenario, the battery would only last for, let's say, 5 years. So there's a difference of 1.5 years in the possible application time of a battery, depending on the operating mode and on the operating strategy of electric vehicles. And that's why we need those simulation models, and that's why we're doing such simulations and for optimizing operating strategy, for considering terminal aspects, for developing new functions of battery management systems in order to increase the lifetime of lithium-ion batteries during operation. So I want to come to the conclusion, to an outlook. I showed you some aging prediction model which we developed, and we integrated this model in our electric energy storages library. The aging is based on an Arrhenius equation, considering temperature, state of charge, and the time. We considered calendaric and cyclic aging. The cyclic aging we considered only with a polynomial function, the capacity loss over the number of cycles. We have implemented some models which are easy to parameterize. So as I showed you before, the Arrhenius equation is very simple, so it doesn't have too much parameters, and you can really achieve some good simulation results and really have some good simulations and predictions about the aging behavior of lithium-ion batteries. And we actually performed some aging prediction based on our initial measurements, which took place 105 days. So in the future, we definitely have to perform some more measurements in order to validate our predicted behavior. The problem is, as we've seen before, the aging simulation took place over 10 years in general, so it's a very long time, and if we would have batteries cycled over 10 years in our infrastructure, we couldn't test any other batteries during that time. So it's very hard to validate the predicted aging behavior. But one approach would be to validate the predicted aging behavior at higher temperatures in order to decrease the battery cycle lifetime, so to have the aging effects at an earlier point of time. And the last point I want to mention, we want to generate a kind of generic parameter sets for our aging models for different kinds of cell chemistries, but therefore we would need as well more measurements, as I said before. So thank you for your attention.